Hello, I'm Rob Simpson. Today we'll talk about generator frequency stability. Have you ever wondered how a generator stays synced to the grid at 50 Hertz, or two generators stay synced to each other? Well, good for you, that's what we're talking about. So the way this works is an overall idea, is that the generators all use a governor, and that controls the slip, which creates a linear relationship between the power and the RPMs. So today we're going to cover keeping the generator frequencies stable together, how they change with difference of power demand, and how they change with, and how the frequencies change when the power stays the same. These are two different calculations that use pretty much the same method, just you're looking for different variables. We'll also discuss briefly the frequency per megawatt demand change. So what you need to know is that a governor linearizes the slip of the generator in terms of frequency, or output frequency I should say, or revolutions per minute with power. This makes the math we're about to do much easier. Generator frequency stability. Now, for our example, we're going to use two generators of equal size. Both of them will operate at 50 megawatts. The first generator's droop will be a 4%, and the second generator's droop will be a 3%. And we will connect these two together and look for a total power of 80 megawatts. Now, the first way we can do this is we can just set them to an equal speed and determine how much power is being used by each. If you draw the power curves as we have here, you will see that the slope represents your droop. Your slope is represented by the droop, and the long side, I'm not quite sure what to call it, it represents the actual speed of these motors. And we will represent that by alpha. And because these generators are connected they're connected, and we're assuming that they're going to run at the exact same speed, they will both share an alpha. The bottom side is the total power, and the maximum power each generator can provide is 50 megawatts, as these are 50 megawatt generators. So we now have two triangles with sides D1, X1, and alpha for generator 1, and generator 2 is D2, alpha, and X2, or in this case, X2 equals 80 megawatts minus X1, which is the total power minus the power from generator 1. So with this information, we can set up inequalities. We know that on the generator 1 side, D1 equals alpha over X1 over 50, or how much of the total capacity X1 is going to use. So it's a per unit value if you're familiar with that. On the other side, we have generator 2, where alpha over X2 over 50 equals D2, where X2 is 80 minus X1. We can set these equal to each other in terms of alpha, and we end up with 0.04 X1 over 50 equals alpha, which equals 0.03 times 80 minus X1 over 50. We can just set these equal to each other instead of alpha now, and we have 0.04 X1 equals 2.4 minus 0.03 X1. A little more rearranging, and we have 0.07 X1 equals 2.4, and with this we can calculate very easily that X1 equals 34.29 megawatts. This gives us an X2 of 45.71 megawatts. So if these two generators are connected to an 80 megawatt load and operate at the exact same speed with their respective droops, we have these operating points. We could also calculate this in terms of the no-load speed adjustment required at the speeder motors if the machines share the load equally. And when we do this, we no longer need to hold the rotational speed of our motors equal. We just need to worry about the total output of energy. So in this case, if they're going to both supply 40 megawatts to our 80 megawatt load, we will have varying alphas. So we'll have D1, alpha 1, and 40 megawatts for our first curve, and our second triangle will be D2 or droop 2, alpha 2, and 40 megawatts. These two triangles can be placed together with alphas pointing towards each other as last time, but they are no longer the same size. So to solve this, we'll use a little bit of algebra. If you recall, the governor linearizes the curve between the motor power and its operational speed or frequency, which is just a y equals mx plus b equation. In this case, we don't really know our y at the moment, and we don't need it. We're looking for the delta y. So we have our slope times our x, which is our power percentage, the per unit power, if you will, plus b. Now b is just our no load speed, so we can represent them, since these will be equal. So since these will be technically equal, we're just looking for the difference between them. We can set this up so that F plus D1 per unit of 1 equal, and then we have these equations. It's very simple. We're looking for 40 megawatts over 50 megawatts, so the per unit is 40 over 50, times our droop, which is 0.04, plus our no load frequency. And for the second motor, we have our frequency again, plus droop 2 times the per unit of 2, which is also 40 over 50. So our second side would be F plus 0.03 times 4/5 as our per unit value. We then are looking for the difference between these, so we end up with F plus 0.03 times 4/5 minus F plus 0.04 times 40 over 50 as well. And this is a percentage, so we'll multiply it by 100%. And with this, we'll end up with 0.8%. And that is the percent adjustment difference in the no load speeds made by these motors when the load is shared equally. And there you have it. That's the basics on frequency and generator stability and control. Thank you, and feel free to share what you've learned today.